All right. Please confirm that my voice is clear and my screen is visible. Somebody please. All right. Okay. All right. So towards the end of the previous class, I was uh, telling you that some of the components of the strain rate tensor are called normal components or normal strain rates, and the other components are called shear strain rate. So 1, 2, 2, 3, and 3, 1 are called shear strain rate components when the indices are different. And of course, strain rate is a symmetric tensor. So S21 and S12 are same, S23 and S32 are same, S31 and S13 are same, and we call the other S21, S32, and S13 also as shear strain components. Whereas normal strain components are S11, S22, and S33. So it's a common notation or way of identifying various components of the strain rate tensor. I was also telling you that omega, which is the average angular velocity of a fluid element, is related to the curl of velocity field, which is del cross V. And the relationship is what I have shown here. Basically, there is a difference of is a factor of 2. Del cross V is 2 times the average angular velocity. So in literature, in books, and later if you take more advanced courses, people will have del cross V, and they will still talk the same about sense of rotation of a fluid element because they differ only by a factor. So if a fluid element is not rotating, then omega will be 0, and so del cross V also will be 0. Or there is a special name for this vector del cross V. It's called vorticity vector. Vorticity vector. And we will use this symbol omega, small omega for vorticity, and large omega for, as I have been using, average angular velocity. Okay. Then I was telling you, in general, these tensors are functions of x and t, and these are also, since they are tensors of various order, 1 or 2, strain rate, and this is W is rotation rate, we can choose to express them in any coordinate system, right? In different coordinate system, their components will differ, but the tensors will remain the same. Now, suppose we choose cylindrical polar coordinate system as our working coordinate system. The S tensor will be expressed in this way, what I am showing on the left side of the slide, left top of the slide. So it will have components SRR, SR theta, SRZ, so on, and these will be coefficients of the corresponding dyads, ER, ERE theta, and so on. So if we are working in cylindrical polar coordinate system, what are the components of what are these components? I mean, individually, what is SR theta and what is SRZ in terms of velocity? Because since it is strain rate tensor, we should be able to express them in terms of derivatives of velocity. So if we want to find that out, what these are, then first we will invoke this definition. Strain rate is symmetric. Strain rate as velocity gradient plus velocity gradient transposed by 2. This is how strain rate tensor is defined. And once you have expressed as in terms of velocity, well, we have gradient of velocity, but velocity is sitting there. Then you can go and use cylindrical polar coordinate system. You write V as VR, ER, V theta, E theta, VZ, EZ, and del as what I have written here. Again, problem number 4 of tutorial set 1. Then you use these two definitions and you simplify. So it will take quite a number of steps. It will take quite a number of steps to simplify it, but eventually you should be able to express this del V in this fashion. Okay, so again we have 9 coefficients corresponding to the 9 members, 9 types of dyad. And once you have written this, then I can match what is SRR. SRR is del V R del R. What is S theta, S theta theta. So you go here and see coefficient of what is E theta, E theta. It is 1 by R del V theta del theta plus VR by R. So in this manner, now we can identify each and every component of the strain rate tensor in terms of velocity, vector, and its derivatives. So I am leaving this as a homework. Please verify that you do get this after you simplify del V velocity gradient tensor. All right. Okay. So with this, I am done with kinematics. And next thing on our agenda will be deriving governing equations of Eulerian velocity field, density field, pressure, and temperature. That I will start in a little while. Let's see if I have questions here. Questions. Okay, I have a couple of announcements. Again, I waited deliberately because I wanted as many students to be here while I make this announcement. There will be a quiz. Quiz number 1. You may remember I said there will be 2 quizzes, each of 7.5 marks out of 100. So first quiz I will have on October 28th. Time will be 2 to 2:20 p.m. So it's a Wednesday. So I'm sure all of you will be available, and it will be on Moodle. It will be based on lecture 1, first lecture, to the lecture of October 23rd. I don't know what will be the number of that lecture, I mean sequence number, but this should be clear enough that whatever we cover till October 23rd, we will have that. And this includes problem sets 1 and 2, which are available to you already, and 3, which I will upload probably this weekend or on Monday. And we will I will also have a tutorial session on problem set 3, so you will have opportunity to get your doubts clarified. So this much will be the portion for quiz number 1. Reference material, as I said, every week I'll tell you where to find reference materials. So fluid element, rate of change, volume, length, etc. What we have done so far, you can find references in Gupta and Frank White, both of them. But if you do not have access to the E version of Gupta and Gupta, at least this you should have. So you can read stuff from here. Frank White, FW is Frank White. Viscous Fluid Flow by Frank White. And the full description of the title of this book is available in the course document, which is on Impartus Backpack. So today, rest of the lecture, and tomorrow we will be dealing with this topic, governing equation of fluid motion in Eulerian description. And for that, again, I have reference here, chapter 2. You can go and have a look. Okay. So all right. So to have the ability to predict the values of these dependent variables, what I have written here. At all x and all t of interest, at all locations and at all times, time instants of interest, we must have the governing equations of these variables, right? And at the end of the day, eventually, those equations are going to, we are going to get those equations by invoking these three basic laws. First is conservation of mass, the second is Newton's second law, and the third is first law of thermodynamics. All right, you are familiar with these laws, but you will see that the form of equation, once you apply these laws, the form of equations that emerge, that will be very new to you. You will find them quite different from anything that you have seen earlier. But bottom line is the equations will be based on these laws. Okay, so let us derive the governing equation first for a general variable phi xt. Okay, where phi xt represents an entity per unit volume. So phi xt, phi is a function of location and time. And again, this is a Eulerian description. There should not be any ambiguity because there is no plus here. And anyway, I have committed myself for Eulerian for the rest of the course. So phi xt represents entity per unit volume of fluid at location x and time t. So what I mean by entity and what I mean by corresponding phi. So if you are talking about, if you are dealing with the entity being mass, then the corresponding phi will be what? Mass per unit volume, and that will be density. So phi is like a placeholder or a representative which can assume different meanings depending on the context. And my idea is first to derive equation, general equation for phi, and then take set entity to be mass, and then get equation for something, then set entity to be momentum, and then get equation for something, and so on. Okay, so that's why I am defining a general variable phi. So entity is mass, then phi will be mass per unit volume, and that is, we know it is density. So I've also written SI units. If entity is mass, it's kg. So its corresponding phi will be kg per meter cube, right? If entity is momentum, uh, of course it has units kg meters per second. Its corresponding phi corresponding to momentum will be, as I said here, entity per unit volume. So that will be rho times v. Rho at xt times v at xt will give me phi xt of momentum, of entity momentum. And in this case, the units will, SI units are kg meter per second per meter cube. Okay. So for every entity, we have a corresponding entity per unit volume, phi. Now, entity can be total energy. Total energy means what? Kinetic energy plus internal energy. So I am not including potential energy here. If there is a flow field where we have a, like for example, gravitational force, I will include the effect of gravitational force in a different way. In a different way, which means I will include that explicitly as a force rather than a potential, right? If you have a force, if you have a conservative force, there are two options to include it in the dynamics. One is that you write the expression for the force explicitly, like mg, we write mg acting on a body. That's one option. The other is you say, no, I want to include the effect of this force as a potential or a potential energy. Then you include it as mgh, and you will add that to the energy of the particle or the body. So I am going to follow the first approach. I am not going to include potential energy associated with any conservative force in energy. I am going to include that force explicitly in the free body diagram. So I am keeping that for later analysis. So right now, total energy I am defining as kinetic energy and internal energy. All right. So internal energy comes from temperature. That's what I mean. by internal energy. So the corresponding phi for total energy will have two terms, again corresponding to the two things that I have here. First is kinetic energy. So the phi for kinetic energy will be kinetic energy per unit volume, and that will be half times rho xt multiplied by dot product of Vxt with itself, right? So this is the phi corresponding to kinetic energy. The phi corresponding to internal energy will be what I have written here, rho xt times Cv, which is a specific heat capacity of fluid at constant volume, multiplied by temperature at xt, right? And you must have come across this expression, internal energy, being written as Cv times T in your whatever course you would have taken in thermodynamics or in class 11th or 12th. You must have come across. So I'm not getting into details of deriving this here. I'm just taking internal energy to be CVT, and thus the phi corresponding to internal energy will be rho times CVT, such that it becomes internal energy per unit volume. Okay, and it will have units joule per meter cube. Okay, so we keep this with us, this idea about phi. I'll come back to it in a little while. So now I will define a new quantity. Again, these will all be useful in when we start deriving the equations. So I'm kind of putting pieces together one by one at one place, and then I will combine them and get to the governing equation. So what is called flux of an entity through a small area delta A in a flow field. Okay, so you have a field, what I have shown here. I have a flow field which is like white space on the paper. I have a reference frame, and now I am putting the reference frame as G. It's going to be, I'm going to assume this as inertial. Well, here right now I don't need it to be inertial, even though I put as G is a general reference frame, because flux can be defined even with respect to a general reference frame. So no, not inertial necessarily. So a frame G is an observer, and you have origin O, point O fixed to the frame G, and then you have a small area delta A, okay, with its normal defined in this fashion. So you can think of delta A, a small area, as a vector, and we define its direction in this way. Okay, En is like this. So En is the normal to that small delta A area. Let us consider a small area delta A with unit normal as En. Now center of delta A is located at X. So wherever center of delta A is, I am calling that position vector reaching to that center as X. And delta A is fixed with respect to frame G. Okay, so delta A does not move in with time as seen by observer. It is fixed. Vxt is the velocity at x at time t, right? Since Vxt represents Eulerian velocity field, you go to any point x, you will have a particular direction and magnitude of velocity there. So that is being represented as Vxt. Okay. So I want to ask a question here. How much of an entity is flowing? Entity means mass, momentum, energy. How much of an entity is flowing through this area delta A? Flowing through means crossing this area delta A along En direction. Okay, due to velocity Vxt. Right, so Vxt is a transporter. You can think of Vxt as a transporter. Velocity is a transporter. It can transport things in fluid. If you if I put some pollutants in one corner of the room and I turn the fan on, uh, the fan will create a Vxt, a velocity field, and that velocity field can take the pollutants from one corner of the room and take to the other corner of the room, right? So that's the question I'm asking. We know that there is a transporter of things, entities, mass, momentum, energy, Vxt. So I'm asking how much transport does V cause across this area delta A in the direction of En. I mean, from going from left of En to right of En per second. Okay. So I want to write an expression for that. So I am taking a specific example uh, of mass here being entity. So amount of mass flowing through per unit area, I am writing like this, and I hope this makes sense. Vxt cosine theta, where theta is this angle, delta A times rho xt. This is the mass that is crossing this small delta A area in the direction of En per second. Okay. Why cos theta? So take the extreme scenario in which Vxt is perpendicular to En. Then what will happen? The transporter is there, but it is oriented in parallel to the surface. So it cannot make any mass cross from the left of the delta A to the right of delta A, right? And the transporter velocity will be most effective in transporting mass if V is perfectly aligned with En, right? So it is important. It's not only important to have V, non-zero V, for transport to be possible across an area of this sort, but it's also important that how it is aligned with the area, and that is the effect which is captured here. Okay. Again, you can check that this is dimensionally sound. It does give us kg per second. All right. So it means that now this is, I have written in as cos theta delta A. You can immediately realize that this can be written in a compact manner in terms of dot product. It's amount of, same question, amount of mass flowing through delta A along En per unit time can be written as local velocity dotted with the normal of the area delta A multiplied by delta A times rho xt. Okay. So this is the mass that is flowing. Now, if I ask the question, what is the amount of momentum that is flowing through A? Amount of momentum that is flowing through A. That would be the first 1, 2, 3 factors will remain the same, and then you multiply that with Vxt. That will be the amount of momentum flowing through delta A per unit time. So this question that I'm asking the second time, amount of momentum, is actually a vector. So velocity is able to transport vectors also. In fact, this idea can be extended to any tensor of any order. It can transport tensors across that area. Okay. So this is the expression for momentum, how much momentum is flowing through delta A. I can ask a similar question, amount of total energy flowing through delta A per unit time, and that would be, again, the first 4 factors will remain the same, and then what you have to do, you have to multiply it by CVT, which is internal energy, plus half V dot V, and then again, I have not written X dot T, X comma T here for as arguments of T and V, but it is implied that it is xt. Okay, so based on this understanding, I am making a general statement here for an entity, mass, momentum, energy, with phi xt as its entity per unit volume expression, or per unit entity per unit volume measure. The amount of entity that flows through delta A can be written in this fashion: Vxt dot En delta A, which is same as what I had earlier. But in the rho xt, I have rho xt and the entity whatever was appearing in these terms, I have combined, and I am writing this as phi xt. So V dotted with En multiplied by delta A multiplied by the corresponding phi of that entity gives you how much of that entity is crossing that surface per unit time. All right, and even though I have put phi here as a scalar, this idea, as I said, can be extended to tensor of any order. So phi can be even a tensor. All it needs to have is it is tensored per the entity, the original entity per unit volume tensor. That's what it needs to be. And then you can make this general expression that this much of that entity is crossing delta A per unit time. Okay. We call this expression as flux of entity. This is what is defined as the flux of entity through area delta A, which has normal En. Okay. So flux is, unit of flux is entity per second. All right. So this will be called flux of that entity through area delta A. In other words, you can put flux of an entity is transport of that entity mass momentum energy across delta A per unit time. And who causes this transport? I have already highlighted, uh, tried to bring it to your notice that the transporter is V. It's like a truck which can carry stuff from one point to other. Okay. So V is like a carrier truck. It can take momentum, can take energy, can take mass. Right. All right. So this is idea of flux. In the total energy calculation, why I said that already, Jitendra. I don't want to include the potential energy there because potential energy will be arising because of the presence of a conservative force, and there is no compulsion in mechanics that you have to include the effect of a conservative force always as potential. It's an option. You can either include the effect of that force as potential, or you can include the effect of that force explicitly in the free body diagram. Like many times we put mg on the body, and I'm going to have follow this approach. Am I clear? Okay. How do we assign a direction to area? That is your call. That it has to be normal to the area, but it can be this way or that way. I mean the way I have shown, or it can be opposite. Okay. For this kind of area, for area, this kind of area what I have shown, you can have it En. It's up to you to define. I have defined it in this way, and based on that, I am saying that flux is defined in this manner. All right. Any other question? All right. So now, armed with these two new definitions and the understanding that lies uh, behind them, flux and this quantity phi, now I want to start deriving the governing equation of phi xt. Okay, and you see, this is the reason I kept it as phi, because whatever steps I'm going to take, like few steps towards its full derivation, uh, those few steps really don't care whether phi is mass per unit volume or momentum per unit volume or energy per unit volume. Those steps will be applicable to all. So I want to just do it once, and then for further steps, I will start taking specific cases of phi being mass per unit volume or momentum per unit volume and so on. So now let's consider an imaginary volume of dimensions delta x1, delta x2, and delta x3, all small. Again, I'm putting them small because very soon you will see I will start dealing with Taylor series expansion, and that's why I want to keep them small, with its center at x1, x2, x3. So this is how I am defining this imaginary volume. The center has coordinates x1, x2, x3, or in the language of vectors, it will be x under bar. and the dimensions are delta x1, delta x2, delta x3, and delta x1. The edges which are delta x1 are along E1 axis, and similarly delta x2 and delta x3 are dimensions of edges which are along 2 and 3 axis. And I am taking this control volume to be a cuboid, means all faces are perpendicular to each other. Okay. Further, I am taking this imaginary volume to be fixed with respect to the frame in context. Okay, so for this observer, of course, fluid particles move, but this control volume, imaginary control volume, does not move. It remains stationary with respect to this observer. So it's like a wire frame. It's like a wire frame that you have put in the flow, and fluid particles can enter through its various phases and leave from some other phases. Fluid flow is left undisturbed. It's just that for our derivations, we want to identify a volume over which we will try to apply governing equations. Right? Uh, this is called a control volume. Okay, this is called a control volume. I will use the acronym CV. So control volume is an identified volume in space, okay, uh, which is fixed at a location, and we will use that for various kinds of derivation. Or I can say that control volume is an imaginary volume in the space in which fluid motion exists, and we focus our attention on that volume. It's a volume on which we are paying attention. We are focusing on. We can call it a control volume. M is the center of control volume. Okay, and I'm putting x1, x2, x3. I'm taking that location to be x1, x2, x3. I have labeled the vertices also. I have TUVW as one face, which is perpendicular to 3 axis, and the other face I have tried to draw as PQRS is the other face which is perpendicular to E3. Okay, I hope these statements make you visualize this better. Again, my drawing is not the best that it could be, but I hope it makes sense once I say put these vertices when you observe or listen to what I said about the faces. Okay, so now I am asking a question. How much of an entity, again mass, momentum or energy, is there currently in this control volume? Okay, how much entity is currently residing in this control volume? And I should mention this, make this connection. Maybe I should have made it 5 minutes ago, but I think it's still not too late. See, whenever we are asking about entities, how much is entities flowing or how much entity is contained in this control volume, keep in mind that all these entities are at the end of the day associated with fluid particles. Okay, so whatever fluid particles do, these entities do. If there is a bunch of fluid particles right now in control volume, so, and since every fluid particle has some mass, has some momentum, has some energy, so we can talk about how much of energy or how much of momentum or how much of mass is there in this control volume. Similarly, when we were looking at flux, I was saying how much of entity is crossing. So keep in mind, I can ask such questions because in reality, fluid particles are crossing. But since every fluid particle is associated with mass, has associated momentum and associated energy, and that's why I can talk about these entities crossing uh, a surface. Okay, but in reality, it's the fluid particles which are crossing. So everything associated since fluid particles are crossing, we can talk about everything that can be associated with fluid particle as crossing mass, momentum, and energy. So how much entity is there in this control volume? So this is the expression I am writing here. You see delta x1, delta x2, delta x3 is the volume of the fluid element, right? It's a cuboid. And phi xt, remember I said it is entity per unit volume. So since this is entity per unit volume, like mass per unit volume, I multiply by volume of the control volume, and it should give me an amount of mass, kg, that is living there. Okay, uh, right? And this should be ideally approximate, because exactly it should be integral, because you may argue that phi xt is changing within the control volume. But I am saying the control volume is so small that to the first order, this is a good approximation, that whatever is the value of phi xt at m, that multiplied by the volume is a good first order approximate of the total entity per unit volume. So this expression will not hold good if I control volume becomes very large. There you will have to do integration of instantaneous phi with delta x1, delta x2, delta x3, and then divided by no, not divide, just integration of local phi xt over delta x1, dx1, dx2, dx3. So we are not getting there because it is a small control volume. All right. So once we have identified this much mass is right now residing in the control volume, the next question I want to ask is, at what rate is this amount changing? At what rate is this amount changing? So right now, if it is 1 kg of, or 10 kg, if this product turns out to be 10 kg right now, 10 kg of fluid is there in this imaginary control volume. Then my next question is, tell me at what rate it is changing. So will it become 10.1 after delta t time, or whether it will become 10.5 or 9.5? Okay, so I'm raising another question. What is the rate of change? All right. So the answer to this question we will get later. I mean, how it is changing. But right now, I want to express this question itself, or the quantity that I'm seeking, in mathematical form. And that mathematical form is, whatever is this entity you found, you should take partial derivative with time, and that should tell you at what rate this entity is changing. The amount of entity contained within the control volume is changing. Right? So why am I putting partial with time here? You see, the explanation would be something like this. Since it's an Eulerian velocity field, phi is being written as x and t. X and t are independent variables, and this control volume is fixed with respect to the ground frame, or the frame in context. So it means x is not going to change. So the rate of change must exclude or must not have any changes in x. And since no changes in x will be allowed, the only change will be in t, and that's why partial with time is the right expression for the question that is being asked here. Okay. And of course, delta x1, delta x2, 3 are constant, because I have kept the control volume. Nothing happens to control, nothing changes as far as the geometry of control volume is concerned. So you can actually pull these out of the derivative, and it is simply sits outside, and the partial derivative is actually acting on phi alone. Okay. So this is the mathematical expression of what the question I am raising. Okay. X is fixed, so that's what I wrote here. X fixed because control volume is fixed at x. Now, to have an equation, so this is really not an equation. I hope you understand. This is really not an equation. This is just a mathematical expression for a question that has been asked in words, using language to mathematics. That's all I have done here. To get an equation, I should equate this expression with something, right? And that something will be actually the cause. Somehow we should know what causes this change. Why will this change? Okay, now we ask the question, what agencies are responsible for this change? If we are able to identify the agencies that cause this change, and we are able to write mathematical expression, that will become the right hand side of the equation that we are looking for, equation for phi, equation for governing equation for phi, right? Okay. So that's the next thing I'll go to. What are the reasons? What are the causes why why this quantity will have a non-zero value? No questions? So whatever would be the reasons, whatever are the reasons for this quantity to have non-zero value, I want to segregate those reasons under two headings. And I call the two headings as reason 1 and reason 2. Okay. What is reason 1? Reason 1, the amount of mass that is contained within the control volume can change because of the transporter's action. Remember, transporter velocity can bring in mass. It can take out some mass from the control volume. So there are some phases of the control volume through which mass may be incoming, but on some other surfaces, the mass may be outgoing, right? So the reason why the amount contained within this control volume of that entity will change could be because of the flux of fluid across the walls of the control volume. So that flux-based reason or transporter-based reason, I'm calling as reason 1. And then everything that is not related, every reason that is not related to flux, something else, there may be some other physics which may cause it to change. I am keeping a placeholder for that as reason 2. Okay, reason 2 is other reasons. We will get to the mathematical form of this later. Reason 1 is because of flux. So reason 1 clearly represents a particular kind of physics because of which amount can change. And right now, I'm going to focus on that and trying to get a mathematical expression for reason 1. And I will use the idea or the definition of, the definition of flux that we had about 10 minutes ago. Okay, so let's focus on reason 1, deriving mathematical expression for this. Okay. So reason 1, I am saying, will take contribution. So reason 1 is how much mass the transporter velocity field is bringing or taking out. And those things can happen on surfaces, right? Flux will be, there will always be an area associated for flux to make sense. So how many surfaces does my control volume have? It has 6 surfaces, right? And I have named them, tried to put S1, S2 like this here. So I think I have, S1 I have. So you see, this is so there are 6 surfaces. I'm identifying them as S1 to S. S1 is the surface which has outward normal along E1. S1 is the surface which has its outward. So now I'm making a distinction between normal. Outward normal is the one which is going away from the control volume. And inward, so every surface here can have you can have a unit normal in 2 ways. You can, for example, this surface S1, what I'm showing, which is a TQRU face, you can have normal in 2 direction. In isolation, you can have normal either in positive even axis or minus negative even axis, right? But here I am saying that this has outward normal as along E1. So I hope there is no ambiguity once I say outward normal. Outward means it is going away from the control volume. Okay, so S1 is the surface which has outward unit normal along E1, and similarly S2 is the surface which has outward normal along minus E1. And then 3 and 4, I am trying to highlight those 2 surfaces which have outward normal along plus E2 and minus E2. Okay, 3 and 4. And finally, 5 and 6 are the surfaces which have outward normal along plus E3 and minus E3. So these are my 6 surfaces. And because there are 6 surfaces, there will be flux of entity because of velocity vector across 6 surfaces. So if I take into account all those fluxes in an algebraic sense, keeping in mind plus and minus, then I should be able to get the net rate at which fluid is accumulating, the entity is accumulating or changing inside the control volume because of all this transportive action. Right, so those individual contributions I am writing as C1, C2, C3, C4, C5, C6. Okay, so C1 is the flux, net incoming flux incoming into the control volume due to surface 1. C5 is the net flux of entity incoming to the control volume through surface pipe. So this is the idea. So let's focus on C1 first. C1 means, this is what it means in language, amount of entity coming into the control volume per unit time due to flux of fluid through S1. So I'm writing coming into the control volume. Okay, so I will put signs appropriately, plus or minus. So amount of entity coming into the control volume per unit time due to flux of fluid through S1. Okay, what will the expression for that be? The expression for that will be what I have written here. So I have V being dotted with E1, and V at what location? Since we are talking about surface URQT, and that surface we know is displaced from the center of the control volume by how much? By delta x1 by 2, right? So we need velocity vector at x1 plus delta x1 by 2, comma x2, comma x3. So this is essentially the velocity vector on surface S1. That must be dotted with E1 multiplied by area of this surface, which is delta x2 times delta x3, and then multiplied by phi, whatever the entity per unit volume is. But then we have to keep in mind that entity per unit volume should also be what it is at the surface S1, and thus I have written x1 plus delta x1 by 2, x2, x3. Now there should be time also. I should have put that because we are talking about things happening at this instant. I have not written it, but and probably on the coming slides also it is missing, but this is implied that we are talking about what is happening at this instant. All right, so this expression is familiar. I mean familiar in the sense the way I define flux and how we interpreted or associated a physical meaning with it. But mind you, I have a negative sign here. Why I have a negative sign? Because you see, if the velocity on this surface is indeed along even direction, then what will happen to the quantity which is within square bracket? That will be positive, right? And everything else is also positive here. If phi is mass per unit volume, it is density, basically, it's also positive. But then I have asked the question coming into the control volume. Okay, and that's why I am putting a negative sign here. I hope this makes sense. So negative sign has to be put if we are talking about, if my statement is coming into the control volume and I'm talking about this surface. All right. So this is the expression for C1. Now I want to ask question. Now I want to write expression for C2. First C2? What is the statement? I mean what it represents? Amount of entity coming into the control volume. So I'm still keeping into the control volume through S2 surface, which is right opposite to S1. Amount of entity coming into the control volume through S2 per unit time due to the flow field itself. I mean due to the transporter velocity. And what will the expression for that be? That expression would be, again I have to dot V with E1. E1 is the direction, and here V should be taken on the left face, on S2 face, so which is displaced from center by delta x1 by 2. That's why I should have V at x1 minus delta x1 by 2, x2 comma x3, right? And the area again is delta x2 delta x3, and the entity per unit volume phi should also come with the same change in argument, because if we are talking about things on the left face or S2, so x1 minus delta x1 by 2, x2 x3. Now see here, there is no negative sign, because indeed when you dot velocity and when I write V in this manner, I take the default direction of V to be along E1. When we write V in this manner and our coordinate system is E1, E2, E3, the default direction or the positive V means going in positive E1 direction. So I hope when you see this statement and see the geometry, it will make sense that why there should be no negative sign here. V dotted with E1 E1 is also in this direction. I mean, as my cursor is moving, E1 is in this direction. V is also by default is in this direction. And if you dot them, you will indeed get the amount of entity entering the control volume. So that is the key. I'm looking for amount of entity entering the control volume. And that's why there is no negative sign required here, whereas here it was required. Because V in this direction, E1 in this direction, is actually taking mass out of the control volume if it is acting on surface 1. But on surface 2, this is this already is bringing in, so there's no negative sign required. Okay. Then we realize that V vector dotted with E1 is nothing but the one component of velocity, right? By definition of the scalar component. So instead of keeping this dot product and under bar V all the time, now I'm just going to take the scalar component V1, and of course it should have exactly the same argument. And similarly, V at x1 plus delta x1 by 2 comma x2 comma x3 dot E1 should be nothing but the one component of velocity at x1 plus delta x1 by 2 comma x2 comma x3. Okay. All right. So we have expression for C1 and C2. So now let's add C1 and C2 and see what is the simplified expression we can get. Okay, so I will take things in pairs. So even though there are 6, what we will see is once you combine C1 and C2, you will get a very simple expression. And then what we can do is it's similar to what we have done in last few lectures, that we will recognize a pattern. C1 and C2 will combine and give some term, give an simplified expression. We will recognize a pattern, and then we can write expressions for C3 plus C4 directly, C5 plus C6 directly. Somebody who is not comfortable with pattern recognition, of course, he or she is free to go and do the full derivations, but we will not do that. Okay, it's 9:51, just 30 seconds. Let me take to complete this slide, and then I will wait for questions. So next we use Taylor series up to first order. Okay, so I'm going to write V1 at x1 plus delta x1 by 2 using the value of the function at base location, which right now is the center of the control volume, which means x1, x2, x3. So writing V1 at the right face or S1 face, S1 surface, using the value at the center, this is the way you can write. And again, this derivative has to be at the center, at the base location. And you can write V1 x1 minus delta x1 by 2, that is velocity, one component of velocity on the S2 face. You can again write using the base value at the base location and using Taylor series, and you will get a negative sign here because here there is a negative sign standing in front of delta x1 by 2, and that's why you will get a negative sign here. Similarly, for phi at right face, at S1 face and S2 face, we can write using the values of phi at the center of the control volume and plus minus this derivative at the center of the control volume multiplied by delta x1 by 2. Okay, so you take these expressions and plug it in C2 and C1, and when you add, we will see tomorrow what we get. We will get a very simple expression. Okay, so I stop here. If you have any questions, I'll be here for next 10 minutes. No, the dot product will not take care of sign of C1 because you have to pay attention to the question I am asking. You see what dot, okay, so suppose I go with your hypothesis that the dot product should take care. What are you dotting with? That is the important, right? I am dotting with E1. I am dotting with E1 in both the cases. If you dot it with minus E1, if you dot it with outward normal in both, then it will take care of it automatically. But I am not doing that. I am writing this dotted with E1 in both cases. So now if you pay attention to only this, the way I'm writing it, if you dot velocity which has default direction in E1, dot with E1, you will get positive. So if I hide this negative sign, you will get positive on S1. But then you see what I am asking. I am asking amount of entity coming into the control volume. But what you are getting merely on dot product is actually something that is going out of the control volume. So to address my question, the language of my question correctly, you have to put a negative sign. I hope it answers your question. Got it? All right. Okay. Any other question? Maybe I'll leave this slide for you to see. So in the last tutorial class, some students requested me to upload the video recording of tutorials as well. I have uploaded, now I've uploaded recording tutorial 2 and I will upload that of first tutorial also uh, during the weekend. And the PDF file of the slides that I use during tutorial sessions, that I have been uploading anyway. So that written matter was always available. Now the video is also available. Yes. So please confirm if entity change through the surface was being discussed rather than dealing specifically with entity coming in, the dot product would have taken care of the sign. Entity change through the surface was being discussed. Parimat, I'm not able to follow your question. I'm going to unmute from my side. Please speak up and ask your question again. I'm not able to understand specifically what do you mean by entity change through the surface was being discussed. What do you mean by entity change? Please unmute your mic and speak, Parimat. Well, I don't know you anyway, so if you are not clarifying it further, then I will answer based on what I understand of your question. So I guess what you are asking is if entity change through the surface. I think what you are actually asking is how much, if the question was only about entity, amount of entity crossing S2 per unit time. If the question was about amount of entity crossing S2 per unit time, okay, right. Well, if you're also to consider entity flowing, yes, yes. If you had to consider entity flowing, if my question was that, tell me amount of entity flowing out of the control volume through surface S2, sorry, through surface S1, then I would not have put a negative sign. Does this answer your question? So, I meant if we were also to consider entity flowing out of the surface. Yes. Yeah, I hope you got the answer. Yeah, if you ask me if I ask the question, tell me the amount of entity flowing out of surface S1, then I would not have put a negative sign there. Yes. If I, so I'm showing on the slide, if I change coming into that underlined statement to entity flowing out of the control volume, I would not have put a negative sign here. So Parimat, are we good? You are, yes, okay. So I have extended the class by 10 more minutes, but I see very few students are left. I'm going to wait for maybe 2 more minutes and then I will close the session. All right, it seems there are no more questions. I am ending the session now.